All right, thank you very much. So I'm going to talk about a project which is not quite as exciting as what you saw earlier with a lot of moving and shaking. This one is like watching paint dry. So this project is about serviceability performance of CLT concrete composite floor systems. I'm Chris Higgins. My collaborators are PhD student Bülent Tunk, Maria Paula Riggio, and Ari Sinha. And the ARS award number is there. Well, let's see if this can go. All right. So a little background on the framework for this research is we're looking at the serviceability performance, and that includes creep, vibration, and relative acoustic performance when we add a concrete topping on top of 5-ply CLT substrate. We're working within a framework of a prototypical building so that we can have reasonable fastener designs and spacings. So our building includes 24-foot spans, again, 5-ply CLT, so that is the primary floor system. It's composite with about the thinnest reinforced concrete slab you can get away with, which is about 2.5 inches. And there's something magic in the ACI code with that 2.5 inches now that you have a continuous concrete diaphragm. We're looking at different shoring conditions because that changes the demands in the fasteners, including if it's unshored, whether it's partially shored or fully shored. And we're looking at a number of different types of fasteners and spacing. And we're looking at both the strength and the deflection limits in these serviceability designs. And so we're looking at the individual connection performance and how that affects the overall system performance. And we're looking at a number of different analytical methods, including basic moment curvature type analysis. Of course, it's nonlinear because of the way the fasteners perform, using the pretty well-known gamma method, as well as nonlinear finite element analysis. All right, so we've done a lot of work looking at the strength characterization of these things. And this is looking at two experiments of two different experiments and looking at different analysis methods. So on the left-hand side, you'll see the moment curvature analysis, where we're looking at the overall load deformation performance. And on the right-hand side, you're looking at whether we use an empirical or we're guessing what the distribution is versus if we know it because we've measured it. And either way, you can get reasonably good predictions in terms of the performance. We have some pretty sophisticated three-dimensional nonlinear finite element models, both of just the CLT, and even if you just want to model the CLT, that's pretty complicated, right? There's a number of different parameters that go into that. And the magic part of this is we're using, in this particular test series, Norway spruce, and the original test data for Norway spruce comes from, it's hard to read here, but 1968. All right, so using known values for the material properties, trying to see if you can't build a model of CLT. And in fact, the material properties from 1968 are pretty good, predicting the bare CLT at this point. Now the next part is we've got to add the concrete, and we've got to make that concrete composite with the CLT substrate below. And so you now have to incorporate the interaction between those two things, including the reinforcing that's inside the concrete and the nonlinear fastener behavior. All right, so the reason for all of these models now is in that framework of a 24-foot span commercial building or residential, what are the demands that are on, the worst demands that are on the individual fasteners, right? And so we're using these models to predict what the let's say shear force that's predictable in the end connector, which has the highest demand. And so we're looking at that, and it turns out that you've got about 1,500 pounds, depending on the design, of the worst load on an end fastener. And then, of course, that's at serviceability, right? Because we're looking at the serviceability performance. And of course, there are other fasteners that are less stressed. So the peak force we're looking at is 1,500 pounds per fastener, and the other one is just 1,000 pounds per fastener. And then you're going to get relative slip that occurs between the concrete and the CLT. All right, so the magic of this now is we want to know what happens to an individual fastener under sustained load, because that creep behavior is going to affect the overall behavior in terms of serviceability performance for stiffness, vibration. There's really no work that we could find on creep behavior in individual fastener. One, because it's really hard to do. Because it takes a lot of time, and graduate students like to try to graduate before you can get to the end of a creep experiment. All right, so we came up with a kind of a clever idea using CLT and individual little cubes of concrete that are connected to it with the fasteners. And then this is kind of a schematic of it. To sustain the force, what we have are some very clever springs that are very forgiving. So if you, they have a lot of stretch. So if you preload them in compression, right, they're going to sustain that force with very little force drop off, even if you have some deformation. And every single spring that we use, and I'll show you a picture, this is what it looks like in the actual laboratory. It's inside an environmental chamber to try to damp out some of the temperature and relative humidity changes that take place. And it kind of looks like one of those crazy, when you look in there, it's kind of crazy looking. But every single one of these includes two. Right, there's a fastener in this one, there's a fastener in this one, and they're in opposition to one another. Every single spring is individually calibrated so that as they creep with time, we measure the amount of deformation, and we know how many turns of the nut to be able to get the force back up to what it needs to be. The other thing you notice is every single one of these has a manually read dial gauge, rather than relying on electronics, because if you have temperature change, your electronics actually drift as well. So we have purely mechanical measurements. So now you've got to take all these measurements on the hour when it's early in the experiment, on the day when you're going into the year of the experiment. And so that's not so easy to then take manually read data and transcribe it and put it into digital form. And so we're using AI, right? So you take a picture and you can figure out where the needle is on the dial, and it makes it a little easier to do that. And here's kind of just an example of what that creep behavior, this is 40 days of creep behavior, not showing you the initial elastic deformation. So this is how it's clearly a nonlinear performance. So in that first hour, you get a lot of the creep, and then slowly it starts to taper out, but they're still moving. We've got about a 50% change in stiffness, right, from compared to the elastic stiffness in 40 days. It's not small, even though the actual measurements are fairly small. All right, so the next thing we need to do is, rather than look at the individual fastener, look at the system performance of those same fasteners and the same different species. And so now we've got a kind of a long-term creep, right, watching paint dry. I could have showed you a video, it would have looked just like, that same dial gauge not moving, right? But if you come back the next day, it's moved just, 10 thousandths. All right, so this is a stack. We've got all of the concrete that you see, the gray here, all of the concrete's in compression, right? But we can get, what do we have, 5s in a stack, plus we've got weight on top of these to be able to look at how they're going to change with time and what the slip performance is along the length. And we got different numbers of fasteners on the bottom, and you can say the weight actually adds up of the specimen. So the most highly stressed one is at the bottom. It has the most fasteners as well. That's what it looks like in the laboratory. Now this has got to stay here untouched for about a year or so, right? So it's got to be protected. We've got a cage of reinforcing steel to keep people from bumping into things. This is a little, you can see how much weight that you've got to stack up on top of those in order to get the fastener demand that we predict in them. This one has a little bit less load because that's targeting that lower value of shear force. And here you can see again, manual measurements of what the vertical deformation is, and well as the slip deformation that's occurring between the concrete and the CLT. And now we wait, except you got to go out every day and take pictures with your iPhone. All right, the other two parts of this, which we're just starting to undertake, are looking at the acoustic performance. And here we're looking at relative acoustic performance, not absolute acoustic performance. So we have, again, two different species, Doug fir and SPF. We've got 3 different types of fasteners. We've got one single concrete 2.5 inch thick. And now what we're going to do is use ISO tapping machine on top to look at the sound transmission through the composite. But we want to know the relative performance. So we're going to do all the ISO tapping of each individual CLT slab before we add the concrete, so we can tell you how it changes with the concrete addition. So we've got microphones underneath as a receiving room to determine what the sound pressures are underneath. The next part is to do vibration. And again, we're using the same specimens for the acoustics as we are for vibration. So we'll have a base understanding of what the vibration characteristics of each of the CLT slabs are without the concrete, and then what the addition of the concrete along with the different types of fasteners that we've got there. And we're doing force vibration on this. We've got a little eccentric mass shaker so we can look at how it performs at different frequencies, as well as doing footfall, for example. And we're showing this as cantilevered. We have some very long substrates that we can look at both negative or the concrete's in tension, as well as when the concrete's in typical compression. And that's all I have. So I'd love to for questions later. Thank you.
Great. Thanks to all our presenters in this section. We're going to have Parker on that side with a mic, and I think Mark is going to manhandle the mic on the other side of the room. So if you have any questions, just raise your hand and we will get a microphone to you. Craig. We do have a few people on Zoom, so I'll pass you the mic just so they can hear, if you don't mind.
Thanks. Question for Tanner. I don't know if Tanner can answer this, or maybe somebody in the audience can, but it'd be really nice to know what the roadmap is for code adoption of the rocking shear walls. Does anyone know?
Ari is going to take that one on. Thank you, Ari. Other questions? Thank you, Ari.
Sorry, Ari.
I thought that microphone was a bit quiet right now. Yeah. Compared to this one. All right. Anything else you want to ask right now, based on anything you heard in this section? Question at the back there.
I was curious for your group, Ari, are you planning to run any of those tests with cementitious underlayment for acoustical to understand how that would impact the weight for the seismic response?
And a follow-up question about which system is there a way to say which one performed the best and which one is going to be the most cost effective in the long run, or is that long term outside of the bounds of the research probably?
Just a point of clarification, when you mention system, it's all the different floor systems talking about? Yep. So we didn't look at the costs, but that is definitely in the near future, somebody will look at it for sure. In terms of underlayment or concrete topping, the first test, which was done in 2017 with the two-story, where that we had timber concrete composite as the diaphragm, where we looked at the different performance of those diaphragms at different seismic level intensity, and how are they, and what are the trade-offs vis-a-vis the acoustic and vibration. We haven't done that analysis, but that is something that can be carried on in the future. Want to add anything, Tanner?
Okay, anyone else have any questions on anything? Any of these? Okay, looks like we're clear. I'm gonna, sorry. Oh, there is a question, sorry.
Okay, I'm in different fields, so I'm maybe it just curious about maybe for Ari about and about the structure, how the steel and the wood can be connected, how they've been combined, and also the issue is about a fire, a possible fire during the earthquake. If certainly, the steel could be currently. I assuming that current high-rise building, they are mostly built by the steel or some concrete combination, and with little wood right now. But if you combine these two, then one of the issue is how reliable they can be connected. Secondly, is about during the fire would be it's an issue or not.
They are issues, but they have been mitigated by tests and code provisions that have been in place for a long time, where you have to clad certain systems, you cannot clad certain, or you have options of not cladding certain systems. The wood and the steel was, the wood was generally connected with steel, and some of it was concealed, some of it was not. There are a lot of other experts in the room from Simpson Strong Tie or other companies that can talk more about it in terms of the history behind and the provisions in code. But a lot of fire tests has also been performed on similar kind of configurations, and it has been demonstrated that the performance was as expected.
Thanks, Ari. All right, we have more time if there are any other questions before we break for an early lunch. There's one up there.
All the research, there needs to be a price indication from doing those research so that you can implement it in real life. So that's one. I have also a question, because this is all referring to taller buildings. How is it? Are you also testing for maybe residential if you're going to build in mass timber?
Does anybody want to have a answer that one? I know that Judith is going to be talking later about modular mass timber housing prototype that is actually in our lab right now, and we'll have the opportunity to tour that. And I don't know if you want to say anything about that now, Judith, or so.
I'll just say quickly that we are developing seismic connections for the tiny little house as well, because anything that's built on the West Coast has to have that. So we have an example you'll see if they're exposed what we're doing now. And I guess I will give you a preview of what we'll be talking about later, is that we're actually next week starting on an optimization process with our engineers, looking at how we can reduce the number of panels, reduce the number of connections, but we'll actually be looking at the seismic connection is a major one, because we know we'll have to do some testing in order to have some performance data so that we can get building permits for it. So yeah, that's coming up at a very small scale.
And to add to that, this is a subset of the research that we have been doing even in both colleges, all three colleges and 2 universities. There's been a lot being done on the light frame side of it as well, which is not showcased here, but there's been a lot of developments on the housing with traditional conventional materials.
Question up the back, gentleman in the green shirt.
I have a small question for the paint drying project that was actually rather interesting. Some say a best practice is to have some sort of membrane between concrete and mass timber for worries of potential moisture leaching. And I guess I wanted to know, forgive me if it was already on the screen, if you did that or if any changes between having a membrane or not would be very consequential in its performance for stress.
Good question. Does it, now I can hear it, okay. That's a good question. So we purposely did not use a membrane. So we cast concrete directly on the CLT, which also means to start your creep test, you have to wait until everything has reached equilibrium, right? The concrete has to cure, and not just 28-day strength, it's got to reach its plateau strength. Otherwise, your stiffness is constantly changing because your material properties are changing. And then the moisture content in the wood has to reach equilibrium as well. So we also don't use any acoustic mat between the concrete and the CLT. So we're looking at essentially the easiest way to put concrete on top of CLT, which is pour it right against it. Actually, we don't see any real problems with the moisture. You're not hosing it down in terms of keeping it wet. We put burlap on it during the early stages, and it's not like you can tell that it's been exposed to moisture. In terms of long-term performance and whether that moisture barrier, I've got a whole bunch of penetrations through that moisture barrier, right? If I've got fasteners that have to connect to it. So the idea that that's going to protect you from long-term exposure to moisture at that interface is probably not true. Anyway. Yeah, if you don't have connectors, maybe it works, right? Bare wood, nothing to enhance the bond. There's going to be some chemical bond that occurs if you've ever used a screed, that the concrete's hard to get off of a 2x4, right? So there's going to be some chemical bond that's in there, but the chemical bond breaks down. In fact, we can see that when we load those individual fasteners. They're pretty stiff. They'll break the bond, and then you're down to just the fastener doing the work.
We have a couple of minutes before we break for lunch. If anyone has a burning question. Yeah, Bob.
Chris, I'm just wondering, I'm wondering if you actually monitor the moisture content in the CLT when you pour the concrete.
We don't actively monitor it, but we know it beforehand, and then we wait till it gets back to where it was before we start.
How long does it take?
Several months. And the problem is it's only at the surface, right, that we can get access to anyway, right? So, but that's one of the reasons to even get a creep test started before you can get to equilibrium conditions, it takes a long time. It's a very paint drying process.
There's another question in the back there. Thanks, Mark.
So I am adding a follow-up question to the question from here. When you are adding concrete layer on the CLT panel, the three surface of the concrete layer are exposed, but the one surface which is attached to the CLT panel didn't get enough time to cure as the other surface. So are you also doing some research on the curing or strength gain or on that layer which is attached to the CLT panel?
Yeah, probably the biggest challenge for the concrete is it's only 2.5 inches thick, right? So you have to make sure that you don't lose too much moisture at the surface, right? So when we form these, the edge has just a plywood formed edge, and that remains in place for the first, I don't know, month and a half, more than 28 days, while we have burlap and then plastic on top to try to retain as much moisture in the concrete. And of course, we're still adding some additional water because it's going into hydration and it's also being lost to evaporation. So even though the free edges appear free, during the curing of the concrete, they're actually behind the formwork. right? So there really is, the only free surface is the top surface, and that's where we have burlap and misting it with water, not flooding it with water.
So I'm interested in the reasoning. I do a lot of multifamily, so of course the concrete overlay along with some sort of acoustic mat is what's sort of required to get your IIC. And so by connecting it, you're violating that. There's no, what exactly do you get out of the concrete overlay by attaching it to the wood diaphragm? You've negated any useful value for acoustics because it's transferring directly through.
All right, so what's the advantage? Stiffness for one. Improved, so much greater stiffness when you add that little 2.5 inches and make it composite. If I just add weight, I mean, that's the other alternative. If you're looking at just acoustics, you use gypcrete, right? So for this one, rather than just add the weight, we want to make it structural because I get much greater stiffness, and stiffness is not a small issue for the spans that we're talking about. And you also get increased strength. That's the primary reason for doing it. Now, the other one is we're looking at the acoustic performance to see if we negate the acoustic performance by doing that. And I didn't talk in detail, but one of the specimens, I mean, we're using them for the structural part, but we want to know whether making that connection really breaks down the acoustic or increases the coupling, right? If that makes sense, to increase the amount of sound transmission to the concrete. So we have one of the specimens there that will have 4 times the number of fasteners, just to see if they're acting as waveguides to increase the amount of sound transmission through the fasteners, not just the concrete. So one is no acoustic mat, but we have a concrete topping without any connectors. So you're just adding mass and however the contact is, because it's cast integrally with the CLT, looking at that performance. And of course, we have the bare CLT by itself as a baseline before we add anything to it. So we can tell you exactly what the impact of adding concrete alone, adding concrete with typical structural fastening, and adding concrete with so many fasteners that it's integral, right? And we'll see whether it will pass or not. But we're not doing any absolute standards, right? We're doing relative performance.
Looking around here, did someone have their hand up over there? No. Okay. All right. Someone just scratched their nose. All right. Oh, there is one. Okay. Up the top.
The test and the product cured. It was an indoor environment just with normal conditioning, not outdoors or in a special kind of space.
So yeah, we OSU is unique in that we have 3 structures laboratories on this campus, right? You're going to see 2 of them today, but there's also the civil engineering structures lab out at Hinsdale, and it's industrial building covered, but we don't have any conditioning per se inside the laboratory, so it's going to get heat changes during seasonal changes, even daily, as well as the relative humidity is uncontrolled. The end of it, and that's where the whole plank beam specimens that I showed for the creep tests are. They're going to be subjected to whatever the ambient conditions are in the laboratory. We've got environmental sensors that are measuring relative humidity and temperature locally at where those specimens are located. But the individual fasteners are actually inside a very large environmental chamber. We're not controlling the environment because actually to try to sustain like the same thing all the time is pretty tricky, honestly. And that probably produces very rapid changes in a short period of time, given the volume of space that you have to control. It's not a little refrigerator. And it's 30-foot long, 8-foot high ceilings, 15-foot wide. So it's a large interior space. But it's at least insulated, and we can damp out the seasonal variation and especially the daily variation. we had electronic sensors on those, and all you see is the temperature change. It's really hard to pick out what the mechanical change is. So that's why we're using it in that way. It's somewhat isolated, insulated, protected from high variability. And the fact that we're using manually read sensors, I think, is the magic part of this. As boring as that is, it's the magic part of this particular experiment. And I think we'll have some really good data that just doesn't exist.
Okay, well, I think we'll finish there. Thanks for all the questions and thanks to all the presenters in this section. I'm going to pass it back to our Master of Ceremonies.